All right, we're still talking about a concave mirror. The light rays coming in parallel go like this, and they come to a point. That point right there is our focal point. So just like a convex lens, a concave mirror focuses parallel beams to a point. The distance from the front of the mirror to the focal point is now your focal length. All right, so if it acts the same, we can make a telescope out of it. So what happens is, light rays come in like this. They hit the mirror, they bounce like this. They come to a focal point. Now, the challenge is, the object's way out here, some star, galaxy, whatever you want to look at a long ways away, but you can't put your head in here to look where it is, because then your head blocks the light. So Newton realized this, and this was Newton's idea. He said, oh, well then just put another mirror in here. So he put a secondary mirror that bounces light out to the side. And then you create your image out here, and then you have to put in an eyepiece right here, and you look in from the side. This is your eyeball, looking in from the side. So this is your eyepiece. Okay? This now becomes your objective mirror. And this is what's called a Newtonian telescope, because Newton invented it. And he did that to counteract chromatic aberration in lenses. So here, let me show you a Newtonian telescope. This type of telescope is very, very common for amateurs because, you can see it here, because they're simple to use and they're simple to make, and you can make a pretty decent telescope pretty cheap. All you need is down at the end here. Can you see that? Oh yeah, you can see that. At the end of the telescope, you'll see the objective mirror at the back. Now this one looks like about a 6-inch mirror. In fact, I have another mirror just to show you. This is an astronomical grade mirror. So you have to have a really high quality mirror to make a telescope. It's not your cheap mirror you buy down somewhere. And the shape has to be curved perfectly to within 1/8 the wavelength of light, which is really, really tiny, which means you have to make this perfectly smooth to about 1/10,000th of a meter. So maybe you got to have it really smooth, okay? And that's usually ground. The final part is usually ground by hand. Lots of times the machine will get it close, and then by hand they tweak it until they get it right. And then they coat it with silver or aluminum, something very highly reflective. And with telescopes, over time that mirror will degrade. And so what you have to do is you have to take the mirror in and then you recoat it again. And that's what they do every few years. Even with the giant, biggest telescopes in the world, they have to recoat them every few years when they're just out to the air. So this is an astronomical mirror. Now these are significantly cheaper than lenses because the light, it doesn't have to go through it. So the back doesn't have to be perfect. The light only hits the front. You only have to make one side perfect. So a 6-inch mirror like this, you can get for $200 to $300. Where a 6-inch achromatic lens will cost you several thousand. So mirrors are cheaper, which is another reason why a lot of amateurs use mirrors, because you can get a much bigger telescope for the same amount of money. All right? And then the eyepiece is over here on the side. This is the eyepiece right here. So the way it works is whatever I'm looking at, so right now I'd be looking at you, I look in this way, light goes in, hits the back, comes out, and right behind it, this circle right here, is a mirror that shoots it out the side, what we call the secondary mirror. And that's what's called a Newtonian telescope, and this is what it looks like from the side, where the eyepiece is up here, light goes in, bounces off there, bounces up, and bounces out towards me. Alright, so that's a Newtonian type telescope. Now we also have, there's another design, which is more common and is probably the most common for very large telescopes. Telescopes that are used by professional astronomers. And this is what's called a Cassegrain telescope. In this case, you have the same mirror back here. You have your objective mirror back here. Light comes in, hits the mirror, like this, and it gets bounced in. That was supposed to be parallel. That was never a parallel. Bounced into the center like this. But instead of coming to a point and shooting out the side, you put it in a secondary mirror that's curved, and it bounces the light back here through a hole in the center of the mirror, and then you put your eyepiece back here and your eye in the back. This is what's called a Cassegrain design. Now, it doesn't, you say, oh, but you have to drill a hole in the mirror. But that's okay, because then you're at the center of it. You're blocking the light right at the center anyway with the secondary mirror, so it doesn't take away any light. You've already blocked that, so you might as well just drill a hole there anyway. And for major telescopes, you never look through them. What you do is you put your detectors, your cameras, your spectroscopes, everything right back here. Much easier to deal with than a Newtonian where it's off, hanging off the side, and your instrument can weigh a lot, and it makes the whole telescope and everything out of balance. The other thing that's nice about this is you notice the light goes in here, bounces out the side. So if you have a focal length that's really long, which was what we want with telescopes, the Newtonian telescopes have to be really long. Where you can make a Cassegrain telescope, because the light is bouncing back and forth, you can make it very compressed, and it doesn't have to be nearly as big. So here is, figure out a way to show it to you here. Here is a Cassegrain telescope. Actually, let me do it this way. I'm just going to move the camera like this. And here it is right here is a Cassegrain telescope. And the Cassegrain telescope, do a quick focus on it here. Is a simpler design because, you see, I'll loosen it up here so I can show it to you. It's very short and compact, but you can see the lens, or the mirror at the back there. All right, here's the mirror. You see this is an 8-inch telescope, so in the back, that's where the mirror is. You can see the mirror in the back. Behind this circle in here is a secondary mirror. So the light goes in, hits the back, comes out, hits this one, then it bounces out the back. Let me turn it this way so you can see it better. And then it hits another lens here, a mirror here that shoots it through the side, and your eyepiece is right here. So you can do it straight out the back, or you can do it on the side. Now the problem with having straight at the back is then you're always bending your neck and it's hard to look at. That's why most people put another mirror in here to shoot it out the side so you're at a more comfortable position. Notice this telescope also has a simple refracting telescope on the side. So when you get a telescope, one of the hardest things to do is the more you magnify it, the smaller the area, so it's harder to find things in the sky. And so what they do is they put a smaller telescope. So this telescope runs at about 70 or 80 power, the big one. This one's about 6 or 7 power, like a pair of binoculars. And there's crosshairs in there, so you line it up in the crosshairs, then you can find it in here. Otherwise, it's really hard to find different objects in a big telescope. This is a Cassegrain design telescope. And most of the big telescopes in the world have Cassegrain or some modification of a Cassegrain design. Even the Hubble Space Telescope was a Cassegrain design telescope. So, next video.